Hello, class. This, I believe, is the 7th in our lecture series. I hate doing these lectures. I just want you to know that. And that's why I haven't done, I've actually done some for some other classes too, but you know, I hate doing these lectures. I would so much rather just be standing in front of you and having an interactive, feedback and class and everything else, but we can't do that. So today, what we're going to look at is we're going to look at frequency response. Frequency response. And I'm originally going to look at frequency response for, let me just get that out of there. Frequency response for the individual 3 components that we use. I'm getting better at these lectures, though. I now have coffee. It's in the morning when I still have my head together. So we want to look at the frequency response of the 3 components: resistors, capacitors, and inductors. And I want to first talk about, if we think about what the impedance of all of those are, R plus J 0 ohms. Let's look at that first. If you look at the frequency response, and I was to do a graph of just the frequency response of a resistor, you would say, okay, well, there is no frequency in there. There's no omega. I don't see any omega in there. In fact, I'm going to, just as a counterweight to that, I'm going to write down the inductance, so the impedance of an inductor. And that, of course, would be 0 plus J omega L. And so what would the frequency response for an inductor be? Well, we know that omega, right? I'll write that over here. Omega equals 2 pi f, right? And so we know that omega is proportional to f, right? There's no f squared there or anything. There's no omega squared. So it's just omega. So it's just 2 pi f, really. I could have written this as 0 plus j 2 pi f L. And we can see how that changes if this is frequency, and I really have this equation here. Let's think about it. 2 pi f L. So what is my impedance going to be if f increases? Well, if f increases, then this whole thing increases, doesn't it? Omega L. So I've got 2 pi f. If f increases but L stays the same, then f is going to go up proportionately. So we could say that as f increases, then also my impedance increases. In fact, that's how we would look at that. That would be Z sub L. And if we looked at Z sub R, I think everybody can see that what we really have is it's constant. Right? It's a constant. Doesn't matter what the frequency is for the impedance of R. Let's look at how a capacitor, I'm going to put the capacitor impedance over here, and of course that would be 0 minus, I'm going to put the minus out in front, now that everybody knows that it's really 0 plus a minus 1 over, or 0 plus j, I'm going to write it both ways. 0 minus j 1 over omega c. And also, this is the way that I conceptually want you to understand it, is 0 plus j, just like I've got 0 plus j over here. But then what's inside the brackets is minus 1 over omega c. And you're probably thinking, well, if I've got 1 over omega c as omega, which is really proportional to frequency, as omega increases, then the denominator is going to get larger, isn't it? So my denominator is going to get larger. C is going to stay the same, but the denominator is going to get larger. Well, what does that look like? Well, if I was to draw, went a little far there. If I was to draw Z sub C as a relationship with frequency, it would look like this, right? An asymptote out to the two lines there, the two axes. So it was asymptote out into the two axes as the frequency got higher. Now that's what they're supposed to look like. And I'm hoping that this is picking up color well enough that you guys can see the red that I'm going to be putting on here. And in fact, even before I do that, what I really want to do is I really want to show you what are these things really like. Because although I say that that's their nominal response, how do they really work at higher frequencies? And that's what I want to point out here with the impedance of the resistor, inductor, and capacitor. So at very high frequencies, and let me, and of course this matters for the value of the resistor too. If I had a very small resistor, you would actually see it follow very much along that lines, right? And then if I had a larger resistor, you would see that it would start to fall off at the higher frequencies. And if I had a very large resistor, it would fall off even slower. So I'm just going to put a little arrow here and write increasing resistance, right? So you can see that it goes this way. As the resistance gets higher, it's much more dependent upon frequency. So if I had a 100 mega ohm resistor at somewhere around 5 megahertz, that would start to drop off significantly, so that by 10 megahertz, we would not have a 5 mega ohm resistor anymore. We'd have about a 3 mega ohm resistor. And you have to be conscious of this when you're designing for high frequencies, because at high frequencies, even resistors have an inductive and a capacitive part of their impedance. Now, you're probably saying, well, does that happen with inductors too? Yes. Remember when we were doing that experiment on inductors, I said really an inductor is a resistor in parallel with an inductor. So we've got a resistance associated with the inductor, and then we also have the impedance of the inductor itself. What I didn't mention was that there also is, and this depends on the length of the leads of the inductor, we really have another very small capacitance that is in parallel with that inductor, and that has to do with the length of the leads. These two leads that are coming out and joining it up to the rest of the circuit, we want to minimize. We want to make those leads as small as possible, because since those have two different voltages, those are going to cause a capacitive value, a parallel capacitive value with that inductor. So this is what we really have. And so you're probably saying, well, how does that then affect the impedance of the inductor at high frequencies? And that's easy. This is what happens. As we start to, this would be the perfect inductor, right? So as I start to go up in reality, with the higher inductances I've got, I'm going to start to have this roll out like this. Very similar to how the response rolled out when we had the resistors too. At higher frequencies, we're going to see. Now, if we just had something that was a very small inductance, right? But the larger the inductance, the more that is going to bend around, right? And so we're gonna see that. So this would be with, uh, I would say, increasing uh, inductance. So with increasing inductance, we're going to start to see that. Now, how about a capacitor? You know, a capacitor also, in reality, is not just a capacitor. A capacitor also has, due to the fact that it's made out of copper. The real circuit that we have for a capacitor is we have an inductor in line with the resistor. Yeah, that's right. It's made out of copper, you know, the everything. So there's going to be an inherent resistivity associated with that. And then we have the capacitor. And then in parallel with the capacitor, we also have a resistance for the capacitor. So I've got a resistance here, inductance here, and that's what the circuit really looks like. And so up to about 5 to 10, up to about 5 to 10 megahertz, it looks exactly like this. And in fact, we can always, if we're working with lower frequencies, we can always say that it's almost perfect. It's almost the perfect capacitor down here. So I'm just going to write that, perfect capacitor, right? But not up here. Up here, we start to find that the inductive aspect of it starts to come into play. And so instead of having something like this at the very higher frequencies, we start to see the inductive loading come back, and we start to see the inductors, the capacitor that is responding more like this than it is like this, right? Which is the way that it's supposed to. So with increasing capacitance, we're going to see that change in that way. Now, I just wanted to bring this out to you because it's something that it's a general knowledge thing that all electrical engineers know, and you're going to be working with electrical engineers throughout your life because electrical engineers and mechanical engineers work together a lot. And that's just obviously the case, right? So what I want to get into now isn't the frequency response of the individual components and how those deviate from theory into reality, like I've shown you here with how these really work at extremely high frequencies. And what I mean by that is 10 megahertz and above. You don't really see a lot of change unless it's a very, very large resistor. You're not going to see a lot of change up until about the 5 to 10 megahertz range. So most of the things that we're doing are much lower than those frequencies, so we don't have to worry about designing for high frequency. But I want you to know about that because when you get out, like I say, you'll be working at the cutting edge of engineering. And at the cutting edge of engineering, we are working with, um, high frequency. So you should know how these individual components um, change with frequency. All right, now, having said that, what I want to do from this point forward is I want to start looking, and this is chapter 15. I hope that everybody has read chapter 15 and 14 and 13 because that's where we are. I'm not sure if I actually had assigned chapter 15, but we definitely are in chapter 15 now. And here's what I want to start looking at is a frequency response of a very, very simple circuit. And this is just going to be an RC circuit, right? So by RC, I mean RC. That's it. just two, an R and a C. And then I want to look at what we can say that this is the ground here, and that's my positive and negative, although we know. So I want to look at this voltage right here, the voltage at A. How does the voltage at A change? And I don't mean just the magnitude, I also mean the phase shift at A over a variety of different frequencies. So the magnitude and the phase shift of um, voltage at A, right? Now, before we start to get into that, what I want to point out to you is that this is a low pass filter. Yep. An RC filter is a low pass. Let's make a little thing here. RC low pass filter, right? CR is a high pass filter. Now, an LR is a low pass filter, and of course an LR would just be an inductor in series with a resistor, and an RL is a high pass filter. So those are your four filters. Now I would have to say that the RC and the CR are used much more often than the LR or the RL filter. And what do I mean by a high pass and a low pass filter? Well, for a low pass filter, let's just look at a graph here with frequency as the x-axis. And should we have the voltage, or should I put the, yeah, okay, so the voltage at A, let's just look at that. So how will the voltage at A change? I'm talking about the magnitude of the voltage at A. I should probably write that, the magnitude. You know, we're not talking about the phase shift yet. We're just talking about the magnitude of the voltage at A. What's the amplitude of the AC voltage at A? And so since I know it's an RC filter, I know that its response to frequency is going to look something like this, right? Low pass. So a low pass filter lets the low frequencies through and cuts the high frequencies off, right? The low frequencies are all getting through, but the high frequencies are being cut off. And so, like I say, a low pass filter is an RC filter. Now, how about the high pass filter that I'm talking about? The high pass filter would be a filter like this, right? And that would let the high frequencies through, and that would be a CR filter rather than an RC filter. And you're probably saying, God, couldn't I put both of these in series and then make a low pass and a high pass, but cut this out in the middle? That's absolutely true. Yes, if you wanted to do that, if you wanted a low pass and then you wanted a high pass filter like this, then you know, you would be fine. In fact, you could say that this was then a band stop filter, right? Because you're going to let this low stuff through, this high stuff through, but the stuff in the middle is not getting through at all. So we call that a band stop filter. Now I could modify these in such a way that I have a low pass filter that then crosses over a high pass filter, you know, one and then the other, and that would be a band pass filter. Let me see if I could draw that. So if I had a low pass and a high pass filter, again, like I have down here, and I ran a low pass through there, right? And then so I let all of that stuff in, but then I put another high pass filter in there. What would actually get through? Really, only the, I'll just have these overlap like this, right? Now, this is going to let everything above there, but we've already wiped out everything above there. So in this case where they overlap, we're going to have only this is going to get through, right? So I have a band pass filter. So I can have a band pass filter, or I can have a band stop filter if I leave some space there. And, you know, but actually that would wipe out the whole thing. And I just, I wouldn't even get this through here. I mean, basically this would wipe out everything. But here's my band pass filter where they overlap. So anyway, let's look at, we've looked at conceptually what these things are supposed to do, but let's look at them at a variety of different frequencies and frequency regimes, and then see how they become a low pass or a high pass filter. Okay? Now, if I look at this, let's just look at the two different impedances that I've got that are working against each other. So I've got Z sub R equals R plus J 0 ohms. And I have Z sub C equals 0 plus J minus 1 over omega C, right? I think everybody can see that. Now we've got really three different regimes. Let's say that we've got a very low frequency, right? So by low frequency, let's say that talking about something like 1,000 hertz. That's a relatively low frequency. So I've got 1,000 hertz, and so we know from what we talked about earlier that if I have 1,000 hertz and I've got 2 pi f radians per second, that's going to be 6,283 radians per second, right? So we can see that that's going to be about 1 divided by 6,283, and then why don't we make C, you know, I'd like to use numbers. I was thinking I was going to do it just symbolically, but you know, I think that you can see it better if we do use some numbers. So let's say that C is a 1 microfarad capacitor. So if I've got a 1 microfarad capacitor, so 1 exponent minus 6 times 6283. Sorry, I was thinking about something there for a second. That gives us that, but I really want 1 over that, and that gives us 159.16. So my impedance for my capacitor is 159.16 ohms. And that would be at an angle of minus 90 degrees. Does everyone see why that's minus 90 degrees? Because it's at the minus there, and it'd be minus J. I can just, once again, put down the complex plane here so that everybody can see what we've got. There's my real, there's my imaginary axis. And so now we know that that's a minus, and this is in the minus J direction. Of course, this is a J direction up on the top. So that would be at minus 90 degrees, right? It would also be at plus 270 degrees, and whichever way that you'd like to write it, that's perfectly fine with me. And then let's say that I've got the resistance here is at 5,000 ohms, right? So we can see that then at 1,000, the resistive aspect would really be the greater, because let's take a 5,000 squared plus 159 squared taken to the square root is going to give me 5,000, right? That 159.16 squared compared to the 5,000 squared is nothing. It's nothing. So that would still give me the 5,000. So we could say that at 1,000 hertz, we're still going to have predominantly a resistive load in this circuit. Now, what if I went to 10 hertz, right? So we've looked at this at 1,000 hertz. In fact, why don't I put that over here? 1,000 hertz, right? We'll make a little table. 1,000 hertz gives us 159.16 ohms and 5,000 ohms. Now, how about 10 hertz? I'm just going to take it to its two extremes now. So at 10 hertz, this is going to be 62,800. Oh, wait, no, I'm sorry. Oh my. It's going to be 6283 radians per second. 6283 radians per second. So if I take 6283 radians, oh, that's 10, yeah. So 10 times 2 pi is going to give me 62.83, right? So 62.83 times 1 microfarad, 62.83 times 1 microfarad, and then taking that 1 over, that gives me 15,916. So Z sub C equals 15,915 ohms at minus 90 degrees. This is, of course, still going to be 5,000 ohms, isn't it? So you can see that at the lower frequencies, the capacitive impedance takes over, but at the higher frequencies, because it's 1 over omega C, the resistive part is going to take over. Does everyone see that? That at the lower frequencies, I've got a capacitive predominance, but at the higher frequencies, I've got a resistive predominance. That's right, and that's what I wanted to show you. You know, we could take it even further. Why don't we go to something like 1 megahertz, right? Let's go to the other extreme too. I don't want you just to take my word for anything. I want you to understand why I'm pointing these things out. So at 1 megahertz, this would be 6.283 mega, right? So 6.283 mega, and then I'd have to multiply that by the 1 microfarad. Oh, I think I screwed that up. Just a second. 6.283 mega times 1 microfarad gives me 6.28. Well, that's not. Oh, 6.283 mega times Yeah, that's right. Times C. Oh yeah, no, I'm right. Yeah, 1 exponent 6. Sorry. And then 1 over. That gives me 0.159 times 10 to the minus 12. So 0.159 times 10 to the minus 12 at minus 90 degrees. And I would still have 5,000 ohms here. So I think everybody can see what I was pointing out is that at the higher frequencies, you're going to have the resistive loading impedance. At the lower frequencies, you're going to have the capacitive impedance that predominates. So now let's look at this, because what I really want to find is I want to find out where R equals X sub C, right? So where does R equal X sub C, which is 1 over omega C, which is, oh, just a second. Oh no, that's nothing. Sorry about that. Something popped up there. So where do those, and of course that would really be 1 over 2 pi FC, wouldn't it? So where do these two things equal each other? At what frequency? Well, let's take the frequency out of there. Let's take it out of the denominator on the right-hand side and put it in the numerator over here, and then take R and put that down the denominator here. So that would just be 1 over 2 pi RC, right? And so let's find that. We actually call this the cutoff frequency. And the cutoff frequency basically shows where we have a fall off of let's see, 37%, right? So I'll explain why it's 37% a little bit later, but let's just look at where that cutoff frequency is going to be. So 1 over 2 pi times 5,000 ohms times C, which is 1 microfarad. And we should be able to find our cutoff frequency. So the cutoff, I'll write the whole thing out. Cutoff frequency is going to be 5,000 times 1 microfarad times 2 times pi. And that equals, well, that can't be right. It's, oh no, oh no, that can't be my, oh, I forgot to take the 1 over. I'm sorry. There you go. Sorry, cutoff frequency is 318.3 hertz. That's our cutoff frequency. And we know some things about the cutoff frequency, but let's just, I don't want to get to that point yet. The fact that we know where the cutoff frequency is and we know how we got to that point where R equals X sub C is good enough. Now, what does that show us? That shows us where our, oh, you know, here's another thing. How do I remember that R sub C, or our RC circuit, is a low pass filter and not a high pass filter? I'll tell you how I remember it. You know, when I was a kid, we used to have this cola called RC Cola, and it was horrible. It was horrible, horrible tasting. In fact, I realized that on Family Guy, they made a joke about RC Cola. I don't know if any of you ever watched Family Guy, but Stewie and Brian, the dog, were lost in the desert. And in the far distant desert, they could see a mirage. They thought it was a mirage, but in fact, it wasn't a mirage. They got up to it, and it was an RC cola machine. Now, they're dying of thirst, right? But when they see that it's an RC cola machine, they refuse to drink it. That's how bad RC cola was. I don't know if you guys had RC cola in your life. I don't even know if they still make it. But I remember the low quality of RC cola. And so whenever I think of RC, I think low, right? So RC is low pass filter. And remember what I mean by a low pass filter. That lets the low frequencies through, and it dampens out the high frequencies, right? Let's say you wanted to get rid of some noise in your design, and there was some high frequency electrical interference noise, like high treble, if you wanted to associate it with the audio frequency. How would you get rid of that? Well, you put a low pass filter that allows the low. In fact, every time that you get on your radio and you're adjusting your stereo and you're adjusting the bass and making that larger, you're just enhancing the low pass filter that you have in your stereo. And every time you get in and you adjust the treble and make that larger, you're really adjusting the high pass filter that you have on your stereo system, right? So that's how we would use these two things. So RC circuit is a low pass circuit. Let's look at the actual stuff here though and see what we're really looking at. Looking at a variety of different frequencies to sort of see how these things would change. Now, if we looked at it at 318.3 hertz, what we know there is that our, Z sub R and Z sub C are both going to be. So at 318.3 hertz, we know they're both going to be the same. So Z sub R equals 5,000 ohms at an angle of 0 degrees, and Z sub C equals 5,000 ohms at minus 90 degrees. That's supposed to be a minus 90. All right, so we've got two of these now. We've got, and in fact, if I wanted to write out my total impedance for the circuit at 318.3 hertz, it would be 5,000 plus J 5,000. Oh, did I say plus? I'm sorry. I didn't mean plus there. I meant minus. And although you're saying, well, that's not going to really make much difference in the magnitude, that's right. But it does make a difference in the phase shift that we are going to calculate later on. So, ohms. You know, if I wanted to write that out as a phasor, I could take 5,000 squared plus 5,000 squared, and then take the square root of that, and that, of course, gives me 7,071. Keeps coming back at you all the time, doesn't it? 1 over the square root of 2. 7,071 ohms at an angle of, now let's think about this. We've got minus 45 degrees, right? Minus, that's a minus there. So minus 45 degrees, or minus 90 degrees and 0 degrees. So what's right between minus 90 and minus 0? That would be minus 45 degrees, wouldn't it? We can use the minuses here. We're not doing complex variables for graduate work yet. The minuses work out fine. We're not taking the square root of that. If we did, then we would have problems, wouldn't we? If I took the square root of this thing, I'd have to use the positive angle. I want you to remember that. Okay, so that's what we've got for the total impedance at the cutoff frequency. So if I made this 100 volts peak, right at that point, and of course, if we wanted to write that voltage at that point, So my voltage out of the source is going to be 100 volts peak, right? And so I could write that as 100 plus J0 volts peak, couldn't I? Or I could write it as 100 at an angle of 0, 100 volts peak at an angle of 0 degrees. So now we know exactly what's going on there, and we could actually find out what the current is. What is my peak current? Because I know Ohm's law. I love to write Ohm's law, by the way. V equals IZ. And let's put a box around it. Don't ever forget that. Oh, and you also want me to write the power equations? Yes, that's right. Power equals VI, right? Or it equals I squared Z, or it equals V squared over Z. And remember, all of these are RMS for power, right? All RMS for power. So let's get back here. So look at our peak voltage. So I've got my peak voltage, or my peak current now, is just going to be my voltage divided by my impedance. So it's 100 volts peak at an angle of 0 degrees divided by the impedance I've got there, which is 7,071 ohms at an angle of minus 45 degrees. So I think everybody can see that I, excuse me, is going to be, well, no, that's not right. 100 divided by 7,071 is 0.01414. Where have we seen that before? Amps peak at an angle. Now let's do the angle. 0 minus a minus 45 gives me a plus 45 degrees, doesn't it? And that's another way that you can always check. If you're working on an oscilloscope and you want to find out what your resonant frequency is, and you don't really know what the resistance and the capacitance and the, whatever is in that RC circuit that you've got, you could easily figure that out, because you just dial it in until you see that current compared to the voltage is going to be at a 45-degree phase shift to the voltage. And when it is, pow, you know that you've got resonance. I mean, you're like a detective, right? So pow, you know you've got resonance, and maybe you know what the capacitance is, but you don't know the resistance. Maybe you know the resistance, but you don't know the capacitance of the circuit. And you're trying to find out what is that capacitance factor in that circuit. And you can do it this way. You can just roll it in on the oscilloscope to get that 45 degrees, and that is your resonance frequency, right? As you change the frequency to get the phase shift between the current and the voltage at 45 degrees, pow, that tells you what your capacitive loading or your resistive loading, if you know the other one, is in your circuit. All right, so that's our current, and that is peak things, and then you can find out what the voltage is at A. So let's just look at the voltage drop. I'm going to write it as a voltage drop. What is the voltage drop across that first resistor? We know what the current is now. We know what the resistance of the resistor is. So we can come up with the voltage drop, because it's just, in this case, IR, isn't it? So for I have 0.01414 amps peak at 45 degrees. There's my current. And then I want to multiply that by the resistance. And of course, the impedance for that resistor is just going to be 5,000 ohms at an angle of 0 degrees. So what we see, once we multiply these two things together, is we get 70.6 0.71 volts at an angle, let's add them, 45 plus 0 gives me 45 degrees, doesn't it? So 70.71 volts at 45 degrees. Now we could break that up too. You're probably thinking to yourself, well, I can already see that at 45 degrees, if I wanted to turn this back into a complex number, rectilinear, a plus jb notation, that I really only have to multiply 70.71 times the cosine of 45 degrees, which, by the way, is 0.7071. So 0.7071 of 70, doesn't that give me 50? That's right. 50 volts plus J 50 volts. That's what we get. So that's my voltage drop. So what is my voltage at A? My voltage at A is going to be 100 plus J0 minus, and then our voltage here, 50 volts plus J 50 volts. Now, don't get me wrong, there's a minus here, so that's got to translate through that second part. So 50 minus, or 100 minus 50 is going to give me 50. Right, so 50 volts. And then J0 minus J50 gives me minus J 50 volts, right? Does everyone see that? So you're probably saying, well, what is that in actuality? I mean, because we don't really care about the phase shift. If we don't really care about the phase shift, then 50 squared plus 50 squared is going to give me 70.71 volts. And now, what's the angle? Well, I got 50 volts going this way, but then I've got 50 volts going this way down here, don't I? So the angle is going to be minus 45 degrees. Minus 45 degrees. Does everyone see that? See how we got that? So we basically we had 100 volts, subtracted 70 volts away from it, and still got 70 volts. So you're probably saying, well, 70.71 plus 70.71 equals 100. Yes, it does, doesn't it? I know, and I remember learning about, negative numbers when I was very young. I think I was like in first or second grade. And I thought that was an epiphany. And then when I started learning about complex numbers and realizing, when the voltage maker, that last lecture that I gave you and showed you how you can get, heaps of voltage out of a circuit that has none to start with. That's right. And that's what we do. We change power around. Sometimes we want to enhance the current. Sometimes we want to enhance the voltage. And so that's what we do. I'm going to hold it here because I'm going to have a separate lecture on where I talk about doing the same thing but with an inductor. And I want to also look at the CR circuit. So I'm going to, continue on with this in some ways. And then I'm going to also point out, we're going to go through the same thing, but we're going to go through it at different frequencies and see what the voltage at A comes out to be at a variety of different frequencies, so that you can see how this is a frequency response circuit. Just letting the small frequency waveforms through and damping out all of the high frequency waveforms. A great way to get rid of electrical noise interference in a circuit would be using something like this, putting something like this in the circuit to get rid of all of that high frequency static noise or whatever. All right. Okay, I'm going to hold it there. I don't know how long I've been talking, but it's been way too long. And I'll put this out, and then I'm going to continue on with another lecture. All right.